So, good morning, everyone. My name is Kostas, and together with my colleague, Professor Kavoulakis, we organize, this series of Athena talks, I think for the fourth year in a row. I would like to thank, first of all, our today's invited speaker, Dr. Giorgos Kourmoulakis, who is a researcher right now in the University of Hillwood University. I have to say that this is something joint that I have with George. I have spent one semester in this very beautiful university and very beautiful campus. Giorgos he was a PhD student in Institute of Electronic Structures and Laser under the supervision of Professor Stratakis. He demonstrates a lot of expertise and research interests, including 2D material spectroscopy, nonlinear imaging, quantum optics, and moiré heterostructures. I'm looking forward to learn what are these moiré heterostructures. The today's talk has a title, Precision Assembly of moiré heterostructures and Exploring their homogeneity. And now, as I said, George Kourmoulakis is a postdoctoral fellow in Quantum Photonics Lab. Something very interesting, I will say, for all of you, since your background is like IT, as I have realized for the moment. So, George, I would like to thank you. Please share your screen and start your presentation. You will have around 40 minutes, and then we are going to discuss with our participants. Thank you very much, George. We appreciate a lot. And as George has mentioned, he has volunteered. If you are interested in the interface between materials and IT, this is the topic to select, and George will help you. George, please share it, make it full screen. Excellent, excellent. Thank you very much, George.
So, welcome everybody. Thank you, Konstantinos, for the introduction, nice words. I'm very happy to be here today, and I'm, as Konstantinos said, I'm a postdoctoral researcher at Quantum Photonics Lab in Heterostructures University, and I'm going to be talking today about our approach to fence with the struggles of people who try to fabricate high homogeneous moiré heterostructures, giving some insights on the whole process. And let's get into it. So this is my short outline of the talk. I will give a short introduction about two-dimensional materials and their heterostructure complexes, just to get ourselves familiar with the concept and why they are interesting, why we try to study them. And then I will get into the processes of isolation and identification of monolayer materials, and then fabrication techniques. And at the end, I will present our wishful thinking towards the autonomous fabrication of high-quality moiré heterostructures. So I'm sure that a lot of people are familiar with this slide in similar presentations. Everything started with common graphite, which is a material that is everywhere in the nature. It's a layered material with carbon atoms in planes held together with weak van der Waals forces. And you can actually use a very simple method that's just a Scotch tape to spread the material around and thin it down. And you can isolate this way one layer of this material. And this is where the interesting thing happens. This one layer has vastly different properties than its bulk counterpart, and it actually demonstrates extraordinary properties. And it is called graphene. So if we take a look at the band structure of graphene, we will see that the valence band maximum touches the conduction band minimum at 6 points in the Brillouin zone. And most importantly, in these areas, there is linear dispersion. This particular thing gives rise to electrons moving in very fast velocities in the lattice. And this gives the ability to graphene to have properties like high mechanical strength, high carrier mobility, high thermal conductivity, among others. And in 2004, Andrei Geim and Kostya Novoselov successfully isolated a layer of graphene and demonstrated these properties. And that is why in 2010, they've been awarded the Nobel Prize. However, there is a drawback, if we can say that it is a drawback. This material has no energy gap. It's not a semiconductor. So it has a lot of nice properties, but its direct implementation in devices, it's not straightforward. That's why the scientific community tried to find alternatives to graphene. And most importantly, they focused on semiconductor groups. And they found several materials that can reach, that can be exfoliated and single layers can be isolated. And one of these family of materials is transition metal dichalcogenides. And these materials are formed with one metal sandwiched in a plane between two chalcogen atoms, as you can see here. And they can reach atomic thickness just like graphene, but they have different properties. If you see here, in any thickness, let's say in bulk form, in 4 layers, 2 layers, they are indirect gap semiconductors. So they cannot give you high efficiency in light emission. But as you thin them down, the band structure evolves and they become, as you can see here in the monolayer, they become direct gap semiconductors. And this actually gives rise to a PL emission from a single layer of these materials. And let's get into more on this, how this PL emission happens. You excite the materials with energy equal or more than the energy gap, and the electron, and one electron is promoted from the valence band to the conduction band, leaving behind the hole. Now, this electron will communicate with this hole via Coulomb interactions, and it will form a quasi-particle that is called exciton. When this exciton, after some time, recombines with the hole, it emits light. Now, the important thing and the interesting thing in the TMD's group is that the excitons of two-dimensional thickness have very large binding energies. They are very stable, very robust. They are the binding energies are at the order of hundreds of millielectrovolts. And this is owing to the large effective mass that they have, the very weak dielectric screening because of the absence of extra layers, and then the space confinement. And if we compare these binding energies to classic semiconductors like gallium arsenide, they are order of magnitude higher. This is why in gallium arsenide, it's very hard to observe PL emission at room temperature, whereas here we can observe PL emission at room temperature because the energy of at room temperature is around 30 millieV. On top of that, TMDs absorb around 15% of the light, in contrast to graphene, which absorbs around 3% of the light. So we can understand that these materials can be excellent candidates for optoelectronic devices. Now, up to date, around 2,000 compounds have been reported to be able to be exfoliated and isolate two-dimensional materials of them, which of course creates a lot of roots for research. And I want to mention to take a walk on the memory lane and to mention one very important thing. While the scientific interest on 2D materials was re-triggered in 2004, there are reports from the 40s about two-dimensional materials and layered materials that can be exfoliated. So in 47, Wallace reported the hexagonal lattice of a single layer of graphite, theoretically, of course. And in the 50s and 60s, there were reports of exfoliation of layered materials. So this is not a new research field, but rather than reinvented, let's say, and our scientific interest is re-triggered about this research field. And of course, We follow the path through finding two-dimensional materials in semiconductors, building the first 2D transistor, going to an area of valleytronics where in TMDs you have a very strong spin-orbit interaction, and there is also a broken inversion symmetry that basically can create, in simple words, a binary system where the role of zeros and ones is going to be played by spin values, spin up and spin down, and you can actually, in principle, store and transfer and store a great amount of information in these materials through this property. I want to focus a little bit more on this particular thing, the heterostructures, and let's get into this. So, reinventing 2D materials, we have the nature's building blocks, basically. So it's only natural to put them together and make complex heterostructures. Scientists are like children. They have curiosity. They want to try new things all the time, even crazy ideas, right? So this led to new physics, let's say, I mean, physics that we didn't expect, and such as interlayer exciton emission of these heterostructures. And interlayer excitons are interesting because, for example, in heterobilayer, they exhibit longer lifetimes because the electron and the hole are well separated. The electron resides in one layer and the hole resides in the other layer this time. And having a longer lifetime, they can withhold more the information that we give them, or we can actually tune them with a twist regarding the twist angle that we induce on the heterostructures, or we can apply external electric field, etc. And on top of that, another group of heterostructures is called moiré heterostructures. And this is a very interesting group. Moiré is a word that kind of sort of describes a large interference. So what happens is that you stack together some materials in certain conditions and you will get an interference in their crystal lattice. And this led to new properties also, like superconductivity, Mott insulator states, ferroelectric domains, excitons that are trapped in moiré potentials. And these moiré materials can be excellent platforms for quantum simulation, studying Hubbard model or similar things. And the most famous one is magic angle twisted bilayer graphene, where we can see vanishing resistance. We can see superconductivity in this material. Now, let's get into details how these moiré heterostructures are formed. So if we have two layers and we superimpose them, and then with a rotational misalignment or a lattice mismatch, we can create this interference effect. This interference effect will create a new lattice with larger periodicity, a superlattice with larger periodicity than the lattice of the constituent layers. And these changes in the real space, in the physical space, will have an impact in the reciprocal space, in the momentum space. And it will change the electronic band structure, and it will affect the optoelectronic properties of these materials, creating, for example, electronic flat bands. In these electronic flat bands, the electron's energy does not vary much with momentum, and therefore the electrons are somewhat trapped, and they can interact with each other strongly, giving rise to all the properties that I mentioned above. So in bilayers, we can have, in these heterostructures bilayers, we can have either a rigid moiré superlattice with a larger unit cell that you can see here, or another thing can happen is for slight twist angles, for very small twist angles, you can have atomic reconstruction. So basically, with very small twist angles, the lattice will try to shift back a little bit to minimize the energy of the misalignment. And this actually creates ferroelectricity. You can have domains where you have out-of-plane polarization. We can see here that the moiré periodicity depends strongly on the lattice mismatch and the twist angle. And if we take a look at an example of heterostructures here, we can see that we compare a homobilayer, which is two same materials, and a heterobilayer, and we see that below 5 degrees of twist angle, for homobilayer, the moiré periodicity goes to infinite, which is normal because if we have 0 degrees, we have a bilayer. We don't have a misalignment. We don't have a superlattice. And you can see here that changing the twist angle, you can change a lot the moiré periodicity. And every time this happens, there is a huge effect on the properties of the heterostructures. And an example is again the twisted bilayer graphene, where you have the magic angle of 1.1 degree, where you have the full effect of superconductivity. But if you slightly go away from this 1.1 degree, you will lose the superconductivity. So let's go back a little bit to understand why we need good quality, high homogeneity moiré materials. So in order to implement them in devices, they have to be homogeneous. You have to have the same, let's say, periodicity all over the surface in order for a device to perform consistently. So, but the building blocks again are 2D materials. They are membrane materials. They are very susceptible to the electric environment, and they can attract all the adsorbents from the atmosphere. They can feel all the stress from the substrate. It's very hard to control that. Also, some pairs of 2D materials has this effect that is called self-cleansing. So they try to minimize energy by creating uniform surface, and they will push away all the adsorbents that are on the surface. But these adsorbents might find some pinpoint positions like a grain boundary, like a defect, like a crack or something, and they will agglomerate there. As you can see here, all the black spots are air pockets that have contamination. And this translates to this thing here. Instead of having a uniform moiré periodicity and a system that will perform consistently the same way, you will have this, where the air bubble that you have here will disrupt on this point the periodicity, and it will also apply local strain that will change the periodicity from area to area. This is not something that you want in a device. There are ways to fight it, like using an AFM tip to iron your sample and push away things. You have to be extra careful to do that because you have to use a very soft tip to not to damage your substrate, your material. And you can also use maybe thermal annealing, thermal energy to move away all these air pockets and the adsorbents. But high thermal energy is kind of dangerous because it's been reported that it relaxes a little bit the twist angle. So if you have a certain twist angle, if you design your heterostructure, your moiré heterostructure, and you want 3 degrees twist angle, and you increase the temperature a lot to create a homogeneous heterostructure, you might deviate from this twist angle and you might lose the properties that you aim for. Now, let's go further back and see how we actually isolate these materials. So the most common way and the simplest way and the way that Gaim and Novoselov used was the typical Scotch tape thing. This is mechanical exfoliation. You have a bulk crystal, you put it on a Scotch tape and you spread it all around to thin it down. And once you do that, you stamp it, you just stick it on the substrate of your choice, and you spend some time under an optical microscope to find the monolayer. Of course, in this situation, you will end up having a lot of other flakes in the same substrate that are of no use. A more controlled way is chemical vapor deposition that you can chemically grow the monolayers. You can end up having a substrate full of monolayers, larger than the ones that come out from mechanical exfoliation. But in this case, up until recently, the materials had a larger defect number than the ones that were exfoliated. And you don't want defects because defects can be the reason why you might disrupt the moiré periodicity. Of course, CVD method actually had a lot of advancements recently, and I think it's getting better and better. There are other ways that, like liquid phase exfoliation, you just get your crystal, you place it on a solution or on a solvent, and with sonication, you break away the crystal, and you might end up with a dispersion of monolayers. But in this case, the monolayers that you will get of that are very small and they're not very easily manipulated. Now, let's assume that we stick to the mechanical exfoliation technique. We will end up with something like this. This is what we see using an optical microscope. We have a 1x1 silicon oxide substrate, 1x1 centimeter silicon oxide substrate. And on this, you will see a sea of flakes, an abundance of flakes. But not all of them are of use. What if you need only this one that is here? 5-10 microns flake that is here. What if you need this? It's clear that you need to spend a substantial amount of time to actually try and find this flake. And it's painful too. So here comes the first part of our experimental approach. And to fence with that, what we do is this. We will do the exfoliation and we will select the flakes that we are interested in, and we will characterize them initially with several spectroscopic techniques like Raman spectroscopy, photoluminescence, reflectance, second harmonic generation, whatever gives us details about the thickness, about the origin, about the uniformity, everything. Then once we do that, we develop code, and this code scans the chipset and automatically identifies the flake that we look for. And on top of that, it doesn't just say where the flake is. You see that I have the coordinates, given that my system will also read the marker and the QR code, and it will give me exactly coordinates of the position of the flake. It doesn't only just do that, but also it gives me details about the surrounding area. This is very important because if someone wants to go and pick this up, it needs to be free. It needs not to have debris around or other flakes. Otherwise, the whole process will be hindered. Now, on top of that, here, for example, the code will recognize that here we have the same thickness of flake, but it's attached to the bulk. So it's of no use. We cannot pick it up. So this code is actually really useful to help us identify exactly, very fast, exactly where the flake of our heterostructure is, and go and pick it up later with pick and place techniques. So every other week, there is a new publication that demonstrates an iteration of these techniques, a new approach. All of them have their merits and their drawbacks. Most of them are based on using polymer films, like you see here, PDMS film with a combination with a PC film. PC film has high adhesion; it can pick up everything. It's very robust in this way, but there is an issue with PC. First of all, in order to put everything down, you need to have high temperatures, which again can relax the twist angle, and you might lose the moiré periodicity. And on top of that, you need to dissolve it with chloroform. And if you induce cleaning with chloroform, you might also induce new contamination to your heterostructure. Another way to avoid, let's say, high temperatures is using PVA instead of PC and dissolve it in water. But again, water can induce moisture to the system that you don't want. I personally prefer this dry technique, and this is the one, a similar one that this is what I use in the lab, where we use PPC. So this here does not need to be dissolved in chloroform. You just need to use temperatures within the glass transition range, which is between 40 and 60 degrees for PPC. In this range, this polymer will behave partially like liquid and partially like gel, like I would say a solid film, but it has high flexibility and high control. You use this temperature to go down and come in contact with your heterostructure or your flake. You pick it up at 40 degrees because you have to drop down the temperature to the limit in order for this to be more solid and pick up the flake without staying down. And then you put everything down at higher temperatures. Now, the temperature that they report here is 110 degrees. I am not using that one because it's dangerous for twist angle relaxation, and also it's dangerous to leave everything down and then have to use chloroform again to dissolve. What I use is 75 degrees, and it actually working. It is working pretty well. Now, most of these techniques are films. So when you go down, you will come in contact at a certain point of the substrate, and then it will create a line, a contact front, let's say, that will progress until it reaches the heterostructure. On the way to reach the heterostructure, it will pick up everything. And you don't want that, because sometimes they will make picking up the heterostructure or the flake very hard. So what you do is this. They will create a dome of PDMS that will confine the contact area, and it will provide more selectivity. So there are a lot of different kind of approaches like this one, and they confine the contact area to millimeter size. They put a high adhesion polymer film on top of the dome, and they pick and place the flakes. Motivated by that part, we designed this one. This is a custom tool. This is just a typical glass slide that you can find in any lab that has microscopes that they use commonly to put the sample on and observe them. And we use a very high precision dicing saw to remove material and make designed geometries like that can give us selectivity on micro scale. And this is how it looks. This is just a pillar on the glass slide, and it has a flat surface. So I will go then and put my polymer on top, and then implement this on a fully motorized, automated, custom-made transfer setup that we have here. So the polymer will conform to the surface of the pillar like that. And it can be easily then used to pick up flakes, as you can see here. This flake is around 70, 80 microns. So you can understand that I have high selectivity in the process here. And the flake sits on the surface of the polymer. So let's see here the control that we have over the process. We have a thin HBN flake here. I come in contact in the center, and I control the contact front basically. How is it controlled? Well, we developed code that calculates the centroid of the flake, calculates the distance from the centroid to the longest edge, and then the code says to the contact front, okay, now progress 10, 15 microns more than that. This way, we manage to have a uniform conformation of the polymer on the flake without taking anything on the polymer. We stop at the location that we want, and then we say to the system, okay, wait now until the temperature drops down to 40 degrees, and then start to retract to pick up the flake. And you can see this process here. It's a fast forward, let's say, video, relatively fast. So it's starting already to retract. We have full control because the motorized stage will move based on the code on very slow speeds. And we can stop and keep going anytime we want. And you will see here, maybe fast forward this to see that until the end, we maintain control and shape of the contact front. And you will see the flake transferred on the pillar here. And we tested that not only for one flake, but for several flakes of different thicknesses. You can see a 5-flake structure on the apex of the pillar here. And we managed to successfully transfer it on another substrate with no problem and no debris. And on top of that, of course, this is just a test sample, but we managed to use the same protocol to create a full heterostructure containing HBN, monolayer TMDs inside, and a gate and a graphene that we can come and do lithography and contact. So this is a rather promising technique and a rather promising customized tool. You will see now here a ring appears on this image. This is basically because the polymer, when it cools down, it creates this effect. It shapes in this geometry. If the flake is smaller, it cannot affect it. But if it's bigger, or if the next flake that you want to pick up and create your heterostructure is bigger, it might create some local strain. So what we have to do is take out the glass, go to a hot plate for 1 minute at 70 degrees, heat it up, the polymer will reshape, will reflow, and it will become smooth again. And then we go for the next pickup. Now, we have a motorized setup, we have the automated recognition of the flakes, we have the automated progression of the contact front. It's not very convenient to take manually out the glass and go to a hot plate, stand there, and then go back in, realign everything. It's very time consuming. So for that reason, we redesigned the glass pillar to this square where we can implement it, we can include it in this customized stage, in this socket. It will extrude from underneath like this. So it's going to be the first thing every time to come in contact with the flakes. And on top of that, we included a ring-shaped peltier that will do in situ reshaping. So we don't need to take it out. We just need to wait for 30 seconds, 1 minute to reshape and then go for the next flake. On top of that, we are trying also to have full control of the conformation of the polymer on the apex of the pillar. This is very fresh. We are trying to etch structures on the surface of the pillars, like this one here, and we are running some tests. So this way, the polymer will drop cast and it will stay within the limits of the structure, and it will create a very nice uniform dome, and we will have high selectivity, and there will be no danger of the polymer to getting off the edges of the pillar this way. So we are running several tests to see what structure is the optimal one for this situation. Now, our ultimate, let's say, goal, our plan is to minimize the input of the users in the whole process. So, of course, the mechanical exfoliation cannot be yet automated. So we will do the exfoliation ourselves. And then we have the automated system that identifies and gives all the details about the thickness and the position of the flakes on the substrate that have the markers. And this will be included in a database. In this database, someone then will go to our graphic user interface, design the heterostructure that they want, having all the details from the automated identification, do the twist angle that they prefer. It's basically ordering, right? And then we will give this order to our automated setup, and it will start doing the process. So one will think you have an automated microscope. How will you align? How will you find everything, especially if there is a pillar in between? So we included this gun sight on the back side of the glass, and the camera will find this gun sight, and it will bring it at the center of the field of view. It will also find the flake, and it will bring it also in the center of the field of view. And this way we are perfectly aligned, the center of the pillar to the center of the flake that we want to pick up. And then the automatic, of course, pick and place assembly happens. And we included everything to this custom motorized setup inside the glove box. And because everything needs to happen remotely, and we did that because we want to avoid any extrinsic disorder in the moiré heterostructures. We don't want to have any adsorbents on the materials. We want to get rid of that. And the reason why we want to get rid of that is this one here. Our plan is to explore the homogeneity of moiré materials and their potential in application in devices from nanoscale using AFM techniques like PFM, LFM, to macro scale, to micro scale, and then macro scale maybe, using techniques like Raman and second harmonic generation. Let me mention that two-dimensional materials, especially TMDs, have very high nonlinear susceptibility, second order nonlinear susceptibility. And you can use polarization resolved second harmonic generation to probe their twist angle very accurately. So to do that, what we do is basically we're trying to understand this method here, which is geometric phase analysis. Basically, you have moiré images, or maybe it's simpler in the one direction thing. You have a non-perfect periodic wave, and then you multiply it with a perfect periodic wave, and you end up with a phase if you low pass filter it, you end up with a phase of your local wave, let's say. And then if you take the derivative of this, you can extract the displacement field. And the displacement field has all the information about the twist angle disorder and the heterostrain that gets introduced between the flakes. And we want to explore this twist angle disorder and the heterostrain in order to aim for a device that is going to be homogeneous in a very large scale. So this is the end of my talk. Of course, I'm not doing any of this on my own. I have excellent PIs, Professor Brian Zeradot and Dr. Mauro Brotens-Gisbert, who lead us. And I would like to thank all the two-dimensional materials team that works with me. Of course, the clean room experts that spend time and effort to help us, and all the quantum photonics lab that creates such an amazing environment to work with. And of course, thank you for your attention.
Thank you. Thank you very much, George. Very beautiful presentation and very exotic research, I will say. I have some questions. If you can stop sharing the screen. There is already one question from our colleague, Pratik. And the question is like, I found it. It was like, where it was like, the question, it was here. Can you please explain a little bit more about the logical representation with spin up and spin down?
On the Valetronics?
Yeah, I suspect. I mean, could be electronics, spintronics,
Yes,
or whatever.
yes,
What do you mean? Can you? So I think that Pratik, you can directly ask the question to George.
yeah. That moment, like you mentioned that like a logical high and low, it's represented by spin up and spin down of the electron or the photonics. Can you please like explain it a little bit more?
Yes. So basically, I guess you want this analog that I made with the zeros and ones. So in these semiconductors have there is a spin orbit interaction that lifts the degeneracy in the valence band maximum and conduction band minimum and creates certain levels that you can access with different kind of spins. And because there is broken inversion symmetry, there are two similar but not equivalent valleys, K and K prime. And you can go with circular polarized light and you can populate selectively each valley, and the selectivity comes to selection rules and spin up and spin down in these valleys. So basically what you can do is you can go and selectively populate one valley and the information will be stored as, for example, spin up, and then you can change the orientation of your circular polarization of the excitation light, and you can selectively populate the other valley with the information being stored in spin down formation.
Okay, thank you very much. Thank you. This was very helpful. Thank you very much, Professor.
Thank you very much, Pratik. I really appreciate your question. There is another question. Sorry, George.
Sure.
From Khalil. What is AFM ironing?
So yes, this is a technique that is widely used. You know, when you do fabrication, not all the labs have the ability to have everything inside the glove box. Therefore, a lot of fabrication happens outside of a glove box in ambient conditions. And I mentioned that 2D materials are very susceptible to the electric environment. So they will attract all the molecules from the atmosphere, all the adsorbents, and you have to get rid of them to actually create a uniform interface. A way to do it is go with an AFM tip on an AFM microscope and come in contact with your material, but a very accurate contact, very soft contact, and scan your material. Possibly, if you have this possibility, in one direction. So basically, what will happen is that your tip will go down, it will start scanning in one direction, it will pick up, it will go again, and it will scan. This way, you move all the adsorbents on one side, creating a clean surface for another flake to be stuck. This is a common method. You have to be careful because you have to use appropriate tips. You need a tip that is going to be soft with a spring constant of around 0.2 nanometers in Newton per meters. If you don't have one of these, you can use a sharper one, but you first have to go to the silicon oxide substrate, blunt it a little bit, make it less sharp, by scanning the substrate, and then go back to the material.
Okay, George, based on this answer, I mean, are you removing the, let's say, these agents, completely or partially? Because by the way that you present it, it looks like it's a mechanical removal, and I thought at the beginning something like electrostatic removal of the
You cannot get rid of them completely.
Okay, exactly.
If they
This
are
is what I
there,
was
they are
expecting.
there.
Right.
What you want to do is you want to push them away to create a bigger surface where you can study in relatively larger scale the moiré periodicity. The moiré scans that you see around are at the order of, let's say, 500 by 500 nanometers. These are not big scans, but your device has to be at least in the micro scale or something like that. So what we want to do is to create a larger device. This is a way to start from zero step, let's say, on a smaller scale to start studying the moiré periodicity and then going forward. The best case scenario is not to have these adsorbents at all, this
But
contamination.
the removal of adsorbents is like an electrostatic or a mechanical?
It's mechanical.
Mechanical.
It's mechanical, yeah. You
Okay.
will see that afterwards, for example, after several scans, your tip, if you go to do some kind of imaging with this tip, you will see a lot of noise. And this noise is because a lot of adsorbents got picked up from the tip.
Okay.
So it's strictly mechanical.
Thank you. There is a question from our colleague, Christina. Thank you for the presentation. I haven't heard about moiré heterostructures before. Where are they used in electronics?
Up until now, we extensively, let's say, study them. Of course, the fact that we can have superconductivity is amazing, but superconductivity, to my knowledge, has not been yet accurately demonstrated at room temperatures. So for these moiré materials. So for now, we are trying to fight this issue that most of these properties are very clear at cryogenic temperatures, but not so clear at room temperatures. So real-time applications will happen, as I mentioned, when we manage to have a device that will demonstrate the same moiré periodicity in all its surface, in all its scale. Otherwise, if you put on a device that will have different kind of moiré periodicities, you will also have non-consistent performance. Therefore, it's not going to be of any use.
Thank you. But do we have any material that demonstrates superconductivity at room temperature right now?
I'm not sure. I don't think so.
I don't think so. That's why,
It's a fun concept. It's a fun concept to think about on these Friday experiments. But yeah, anyway.
Thank you. Then we have another question from Emin. In the context of electrical and optical properties, what advantages and disadvantages these structures have compared, for example, to pure graphene? I mean, George, the floor is yours.
To graphene.
To pure graphene, yes. I mean, I think that you mentioned this at the beginning of your talk, that here we can create a band gap, whereas in the graphene, we don't have a band gap, for example.
Yes, exactly. Graphene is a semi-metal, which means that you don't have a current on-off ratio. You cannot control how the currents will move. You can create a band gap in graphene. If you partially oxidize it, you can start opening a band gap. But then again, the semiconductor band gap that the two DTMDs have is short. It falls within the visible range. It has all these kind of properties that you can readily use to go through certain, let's say, development of optoelectronic devices. Graphene is a very nice thermal conductor. It has high carrier mobilities. You can use it in different kinds of applications. It's not better. TMDs are not better than graphene. Graphene is not better than TMDs. They complement with each other. For example, graphene has the way that the electrons move in graphene lattice. You can use it maybe for terahertz antennas because they can find positions where they can deflect it and they can be applied in certain other areas, let's say.
I totally agree. For example, graphene is an excellent electrode. For example, we talk about
You saw in the heterostructures that we always put graphene as a contact there.
Yeah. There is another question from Hassan. Hassan, please ask the question directly. This will help.
Okay, so
Thank you,
so in your setup, you showed a glass pickup and drop off setup that you pick up at 40 degrees Celsius and drop off at 75 degrees Celsius, the flakes, but you did not show any adjustment for the angle adjustment. So how do you actually create the moiré pattern if you cannot adjust the angle or rotation of the flakes that you're dropping off?
So I demonstrated here just the first pickup, but when you go, for example, you have already one flake on your pillar and you go down to the second flake and you need some twist angle, in our customized transfer setup, we have a motorized automated stage underneath. So in the graphic user interface, you already give the order of the twist angle, and then it will rotate accordingly to do that. Now, one would say, how do you know about the degree? How do you design it? What's the point of how do you find which angle you need with respect to the shape of the flake? So normally, the longest edge of the monolayer TMDs is zigzag orientation, is a certain crystal orientation. We take this as a reference, and with this as a reference, we do the twist angle. The best way, this is not a very good way because you just assume things because of what you see. Sometimes the monolayer might break in the middle and you don't identify the longest edge accurately. The best way is to do first nonlinear imaging, because nonlinear imaging probes the crystal orientation of the material, and then you know exactly, and then you go the twist angle alignment. And to go further, because the system that I described here is not showing that, but we are developing an ecosystem that will have both the database of the flakes, a robotic arm that will do the pick and place assembly, and we are developing also just next to it the characterization system that has second harmonic generation and Raman. So at the end, you will have a product that you can readily identify whether you achieve the twist angle or not.
And George, I suspect that the nonlinear imaging, in order to identify the orientation of the crystal, is based on the phase match angle. Am I right? So you need to do a phase matching in order to have the higher efficiency of the nonlinear process. And by this is very much related with the direction of the axis, the optical axis of your material, no?
Linear polarization of the excitation, and you probe the crystal orientation directly. You can probe the armchair orientation this way. I think there are a lot of works on that matter, a lot of things that Dr. Dimitrakopoulos is doing in ISL on that matter, and we collaborated and had several publications with him on that. Dr. Ioannis Paradisanos too demonstrated that. So it's really simple. You just rotate the linear polarization of the excitation light and full degrees, and you probe the armchair orientation.
Yeah, but
you will see the contrast.
Yeah, but what do you observe is the phase match angle in order to have the
yes.
So the floor now is to our colleague George Kavulakis, and then I will go back to the question from the students. Thank you, George, for waiting.
Well, nice presentation. Thanks a lot. First of all, could you tell us some more about the superconducting phase of these heterostructures? First of all, what is the critical temperature in your system?
We are not studying superconductivity at all, to be honest. This is we are focusing more on the TMDs rather than the graphene-related moiré heterostructures. So the TMDs will show, for example, ferroelectric domains on certain twist angle, and we probe them with the piezo response force microscopy. But we don't study at all the superconducting moiré heterostructures. I know that it should be pretty low. but I don't remember exactly the value.
So I mean, these are supposed to be the old-fashioned BCS superconductors. Are they high-temperature superconductors?
But by high temperature, you mean which range, let's say, of temperatures?
Yeah, all these, well, they must be around more than 100 Kelvin, I think, 150.
I find it hard to believe that it's gonna be there.
Yeah, okay.
I don't think so.
Okay. And another question, just from curiosity, in case you know, you mentioned that the linear dispersion relation in the case of graphene gives rise to these peculiar properties. Do you have a simple argument why this is so?
The linear dispersion basically allows for the carriers to move in somewhat relativistic velocities in graphene, not speed of light, first, but they behave like massless Dirac fermions. They are like waves. So these actually make them interact with each other a lot, and there is, I guess, the orbitals that are formed, the sp2 hybridization that are formed in graphene are responsible for all these properties, the mechanical properties, depending on the orbitals that are in plane or out of plane. We talk about these are the ones that actually give rise to the mechanical properties and the conductivity properties.
Okay. Well, thanks a lot again.
Thank you.
Thank you both, Georges, for the answer and the questions. There is one more from Khalil. I have another question. How scalable is the technique really? And if it is not very scalable, why invest so much time and effort in automating it? Good question, no?
This needs a lot of discussion. So let me paint you the picture of my life the past 5 to 10 years. So I will go to the lab, I will take a bulk crystal, put it on a scotch tape, do the thinning down, stamping on the substrate, and then I will spend 2 or 3 hours trying to find one flake in the sea of flakes in one substrate that will have the thickness that I want, the dimensions that I want, that is not gonna have any cracks or contamination or disorder, or it's not gonna be attached to a bulk. So this takes a lot of time and effort, right? Then you find only one flake. What if you want to build a complex heterostructure with several flakes? This multiplies the time and the effort that you put there. So we have to fight, we have to fence with that issue. We have to push towards making this whole automated process scalable in order to, at the end, save all that time. It is, there are a lot of things that can go wrong during the process, and this is why I showed in several locations that we do iterations of things. We change the design of the pillar, we do some corrections on the algorithm of the code that identifies the contact front, for example. But at the end, I believe that we can reach a point where we can demonstrate soon a fully automated process where we can construct a full heterostructure ready to be studied. I'm pretty sure that we can do this.
Thank you, George. I hope that our colleague Khalil is satisfied, or if not, please come back. And I have, before we finish, I have a couple of questions. George, first of all, is this twisting can happen, twisting between the heterostructures, that it has an impact, as you very clear said, in the periodic distance, which means impact in physical and electrical properties. Is this twisting can happen in real time? Can you observe this twisting, and can you impose this twisting at the same time that you can take a measurement?
Yes. So there is, so these materials, we have to remember that they have high lubricity. They are lubricant materials. Molybdenum disulfide, for example, was used to be is still you can still purchase molybdenum disulfide as a lubricant material. Their high lubricity allows us to go with a certain tool and in situ twist the angle. So it is definitely possible, and we do have a project that we try to do that.
Which means that, for example, I suspect that because the 2D materials, the number of the layers you have, it controls the energy band gap. So by using these heterostructures and by moving and having a band gap, this can tune, let's say,
You can have tunability,
detector.
yes, exactly. So
Okay.
if you have, for example, a heterostructure and you go on top and you start twisting the top layer, you effectively in real time tune the band structure because you change the periodicity.
Yes. And what other parameters do you have for fine tuning? You mentioned something about temperature. So if with a fine way you tune the temperature, also you can fine tune this periodicity. Because if you do too much, you said that you are losing, all this.
Yes. So temperature is used to relax a little bit the strain in certain reports, but I find it for large twist angles, it's okay, but for small twist angles, it's a little bit dangerous because you might relax back to where you don't want to be.
So I suspect that the twist angle provides you somehow a tolerance measurement of how many things you can do in order to tune your heterostructure. Because if you have
yes, exactly. So basically, at the end, if you don't have any contamination on anything, what you study in these moiré heterostructures is the twist angle disorder and the heterostrain. The heterostrain is the local strain effects in the interface of the two materials that have the moiré superlattice. So the twist angle plays a huge role, of course, because for any given angle, you effectively change the moiré periodicity, you effectively change the band structure, and this will have an impact on the properties. And it will lead from one state to another just within the few degrees of freedom.
Do these materials demonstrate piezoelectric phenomenon?
Yes, they do. So in materials that have slight twist angles like 0 or maybe 60 degrees, depending on the symmetries, this difference, you might get atomic reconstruction, let's say. What's atomic reconstruction? Basically, the material will try to minimize the energy due to the misalignment, and it will shift a little bit, and it will create domains where you will have out of plane ferroelectricity with different kind of polarizations. And you can go with PFM, for example, you can go there and you can measure the amplitude of the ferroelectricity, of the ferroelectric domains. You can see the walls, and you can also see the phase. And not only that, you can apply bias to the tip, and you can change the phase to your liking. You can tune it. And of course, on top of that, because it's a piezoelectric phenomenon, if you apply also strain, you can effectively tune it too.
Yes. I was expecting this.
Yeah.
All right. I would like to thanks again all of you for your participation. Moreover, for your questions and the discussion that happened. This is the most important thing in any presentation. I would like to thank again Dr. George for his nice and clear presentation. This is also very important for me. And let's meet again next time. We are going to have a professor from the Technical University of Crete. She's going to speak to us about spectroscopy. And let's renew our meeting next Friday. George, my greetings to Scotland, to the most beautiful small country in Europe, as they used to say in Edinburgh Airport. And
Hi.
stay safe. Bye.
Thank you very much. Thank you very much.
Thank you very much. It was an honor for us. Bye.
Me too.